In our introductory video, I went through and explained to you just some of the terminology and the shape of your two basic sine and cosine functions, which are going to be now the key components to kind of the heart of the unit, which is what we're going to get into today in this video. We're going to look at how do we actually draw the sketches of these sinusoidal functions, whether it's a sine function or a cosine function. So just to refresh your memory, we went through this kind of standard form and developed it in our last video, where the number in front, we said it will control whether the graph is reflected in the x-axis, and will also affect the amplitude, which was the height of those waves. The k value is going to have an effect on the period. You remember it was always the reciprocal for this one. So your horizontal stretch factor from our function unit, stretch factor, was always 1 over that value. Well, if a regular sine function or cosine function, remember, let's just take sine for example, started like this, went like this, it started at 0, it was finished its pattern at 360 degrees, so it had what we call a period of 360. Well, whatever this number is, that will be the new fraction that you're going to use to figure out the new period. So it's basically going to be, so if that's a 2, it'd be 360 divided by 2. It would now take 180 to complete the same pattern. If it's a 3, it'd be 360 divided by 3. If it's a 4, it'd be 360 divided by 4. So in general, the period of a graph, the period, is always in degrees, 360 degrees, divided by whatever that number is right there, your horizontal stretch factor. If it was in radians, this would change and now be 2 pi instead of 360 degrees. Phase shift, that's found in here. So a minus c would move the graph c units to the right. If that was a plus c, it would move whatever c is c units to the left. And then at the end here, we have our vertical translation. So a plus d moves your graph up d units, and a minus d moves your graph down d units. And recall from our unit on functions, if you were doing these with transformations, you always look for reflections first, then stretches, and the last thing you examine are translations. From that notation, try and get them both together here, you should be able to write a mapping. Again, we did this in unit 1. So if we were to take regular ordered pairs, x, y, from our base function, which in these graphs will be either sine x or cosine of x, and come up with a mapping, well, the x values, or the theta values, if you look here, we're going to, our stretch factor will be applied to the theta values, again, or the x's. It's going to be 1 over k multiplied by your original x value. And then if it's a minus c, it will be a plus c. So these numbers up here, the ones in the bracket, these affect the x values. And then these two on the outside are going to be the ones that impact your y values. So in A, here, we said that's going to be a vertical stretch. Well, that's going to make the y values either get bigger or smaller, depending on what kind of number that is. Or it could flip them, switch them from positives to negatives, your y values. And then this number will move them up or down. So then if you look under mapping, so it's 1 over k, theta plus c, and then it's the number in front, so your a value multiplied by your y's. That'll make your y's bigger, smaller, whatever, depending on this. And then this will move them up or down. So in Unit 1, when we talked about functions and mappings, we wrote them out. I'm not sure we used them for a whole lot of any benefit to us at this point. Well, starting in this video, you're going to see the real value of being able to write out a mapping and then understand what you can use them for. If we just take this function here and we just try and identify its properties, let's just fill in this chart below. So if I look at this function, So let's start with the domain. So the domain is, remember, domain is any number on here that your graph could take on. Well, there's nothing on here to say the angle couldn't be any numbers, any particular value, so it could go the pattern forever in both directions. So we say, well, theta could be any element of the real numbers. Now, the range. This one you got to kind of think your way through it. So the range, we're talking about what's the highest number on the y-axis and what is the lowest number on the y-axis that our graph will be able to take on. You're going to look two places. You're going to look here. The negative really doesn't matter because it's just, it flips the graph. I get that, but it really doesn't matter because if you have it at +2, it'll flip it down to -2. The negative is immaterial. It's this number, the 2. So the 2, if I look at that, that would mean the graph's going to be up at 2 and down here at -2. Well, you say, okay, well, the range is between -2 and 2, which would be true, except then at the end, you got to remember we're going to now take that graph and move it down 2. Well, if I do that, this top number, if I move it down 2, is now going to be at 0. And if I move this one down 2, it's going to sit down here at -4. So you're going to see that this graph, which was running between 2 and -2, is now going to make a wave that's going to pass between 0 and -4. So your range will be -4 is less than or equal to y, which is less than or equal to 0. Or, if you prefer this notation, -4, comma, 0. That means everything between -4 and 0. All right, reflection. Look here, say yes, there is a reflection, and it is reflected in the x-axis. Amplitude, so that's how far is it going to be from the sinusoidal axis up to the high point or down to the low point. It's always this number right here. Ignoring the negative. Amplitude is always positive. Horizontal phase shift in your graph, right in here. So this graph, because it's a +30, is going to go left 30 degrees. Always make sure you indicate the direction as well. Don't just say +30. That doesn't indicate you know whether that means left or right. Use the actual word left or right. Same with vertical translation. Always say up or down, whichever it is. So when I look at this one, I can see that it's going to move down 2. And the period, well, normally a regular sine function takes 360 degrees to make its full pattern. However, this one's got a number in here, so that's what we call the k value. K is equal to 3. And we found that the period is always 360 degrees divided by k, which in this case is 3, which means this graph is going to have a period of 120 degrees. Now, a student will often mistakenly write it down here in this box. They'll say the period is 3. They're looking in the right place, but they don't understand that that's not the period. That's the factor that's going to allow you to determine what the period is. So in this case, that turned out to be 120. Now, one thing that I didn't ask for here that I normally would have is the equation of the sinusoidal axis. So where would the middle of this wave be? Well, if you did this part here, that can be answered for you because the original middle of the wave was here, and we moved everything down 2. So the middle of the wave, which was at y equals 0, well, it's now down here, across here, and it's now at y equals -2. So your sinusoidal axis would be the equation y equals -2. So an easy way to find it is that it's always going to match up with your vertical translation. If your graph moves down 2, because your sinusoidal axis is normally at y equals 0, so if you move it down 2, everything's moving, so this is going to move down 2 as well, and it's going to now be at y equals -2. If that was a +7, it would take your sinusoidal axis up to y equals 7. So it's always going to be y equals whatever your vertical shift is. So that's kind of the properties we were talking about in video 1 and how to pick them out from a function. Well, the next part about this is how do we actually graph this? think that's the same function. So we're at the point, we already filled that in, we're at this point. So now we're going to look at graphing this. So how do we do that? Well, to do that, we're going to use a strategy referred to as mapping. And the way you do it is you have to identify the base function. So in this graph, I would identify my base function. You look here, you see sine. So you know that y equals sine theta is the base function. So you need to know, what does the base function look like? So this information that you see here is not going to be provided. You need to know this stuff. So you would have to know that the sine wave starts at 0, ends at 360, and basically you'll see these 5 red dots. Those are the key points you should know, and you should know them already. This is all you're knowing is that, so this is 0, this is 90, this is 180, this is 270, and this is 360, every 90 degrees. Now this has been nicely generated for you on a computer. If I was going to show you a way to do this by hand, just that, and let's see here. Yeah, so let's suppose this wasn't here. You say, well, how am I going to do that? How am I going to make that little graph if it's not given? Well, what you're going to do is you're going to say, here's my base graph, y equals sine of theta, and you're going to make a little axis like this. And here's the strategy we use. So we go out to the end, and we just put a little line. And we cut it, so just eyeball it, doesn't have to be perfect, this is just a sketch. Cut it in half. Then look from there to there, cut that in half. And then look from there to there, cut that in half. And then if you do that right, you should have 4 blocks here that are roughly about the same width. Put your highest point up here, which is 1 right now, and your lowest point of a sine wave is -1. And then this is now, so there's 0, this is 90, this is 180, this is 270, and this is 360. And I know that the sine of 0 degrees is 0. The sine of 90 is 1. The sine of 180 is 0. The sine of 270 is -1. And the sine of 360 is 0, giving me a wave that would look something like that. So then you go down here and you identify these 5 key points, which are up there on my graph. So 0, the y value at 0 is 0 on a sine wave. At 90, you can see you're up at 1. At 180, you can see you are at 0. Now then 270 is going to be -1, and 360 is going to be back at 0 again. So 270, you can recall, was at -1, and then this one was back at 0. Well, we're going to write out the mapping rule that would go with this. So we're going to go with, so theta instead of x, I'll just call it theta, but you can put x there, it really doesn't matter. Theta, comma, y, those are my base points. What am I going to do to them? So this is the symbol that means maps to. And now you're going to write out the mapping rule that would turn this base graph into this new function. So it's, again, same thing we did in Unit 1 on function transformations. Start with the 3. We're going to take a third of all of the original angles. We're going to move them left 30. We're going to multiply all the y values by a negative, and we're also going to double them. So we're going to reflect them and multiply them by 2. And we're also going to move them down 2 because of this -2. So that's called your mapping rule. So then the premise of this is we go down here. All right, so we're going to take our base points, which are these ones, from this base function. We're going to feed them, basically feed every ordered pair in here, and then it's going to spit out the new ordered pairs where they would be situated on this function up here, this one, which is the one we're trying to graph. All right, so here's how it works. I'll maybe write out the first couple, but we're not going to do this. We're just going to do it in our head for the most part. So the first order pair is 0, 0. That means you're going to fill 0 in where the theta is. So it's 1/3 of 0. You're going to subtract 30. Well, 1/3 of 0 is 0 minus 30. So the new theta is negative 30. 0 is your y value. It goes in here. So comma, negative 2 times 0 minus 2. Well, negative 2 times 0 is 0. Take away 2 is negative 2. There's 1 point. We got to do that 5 times. So 90. 1/3 of 90. 90 is going in here for theta. So 1/3 of 90 is 30 minus 30. That's going to be 0. This time we're going to put 1 in for the y. So negative 2 multiplied by 1 is negative 2. Subtract 2 is negative 4. Now we'll go to 180. 1/3 of 180 is 60. 60 minus 30 is 30. We've got 0. We already did 0, so we know the answer is going to be the same as up here. So it's minus 2. Now at this point over here with your angles, after the first 3, you should have established a pattern. If you haven't, you've screwed up. Negative 30, 0, 30. You look and say, oh, look at that. I'm going up by 30, up by 30. Now I say you should always do 3 because you might screw the first one up. So don't just assume that you've done this one right. Do 3 of them. And if you got your pattern on the go here now, you can fill these ones in and say, well, this one's, without me even doing anything, that's got to be 60. And that's got to be 90. You can check it if you want, but that's what's going to happen. Because this will set up, it's basically setting up a scale for you on the theta or the x-axis. Now these ones here, we've got to be careful because we haven't done negative 1 yet. So let's put it in here for y. Negative 2 times negative 1 is a positive 2. Take away 2, that will give us a 0. And then if I do 0, which I've done already twice, I know that I'm going to get negative 2. Well, the good thing is if you look at this, the lowest number y ever goes is negative 4, and the highest number y ever reaches is 0. If you remember when we filled in the range, that was our range. It was from negative 4 to 0, which is good. Our graph's at least matching up with what we thought was going to happen. So then you're going to take, and you're basically just going to graph these 5 points right here. Now, the easiest way to do it, I used to use this grid format, but it's actually a lot easier to not even bother with the grid. You need to remember these are just sketches. They're not designed to be anything too complicated, especially with the technology that's available now. We know that we can fairly easily graph what this would look like. I'm actually going to do this one on Desmos here in a moment. Okay, so here's what you do. You just draw any old horizontal line. That's going to be your x-axis. You're going to always cut it in 4. So go to go here. And again, this is why I find it easier if you don't actually have graph paper. You just do it in your notebook on any sheet of paper. So you draw a straight line. Don't make it too small. You don't want to make it too big. But you just need to, you're going to show one cycle of the wave. So put a number here and here. That'll be your start number. That'll be your end number on your horizontal scale. We'll come back to that in a second. And then, like I showed you earlier, go to the middle first, just so you get your points roughly the same width apart. Cut it in half. Estimate that. Cut that in half. Estimate that. Cut it in half. Now put your scale on here. So if you remember, our scale was going by 30s, and it started at negative 30. So this point right here is negative 30. That's 0. That's 30. That one's 60. And that's 90. Now the y values run between negative 4 and 0. So your y-axis goes down through 0. Now this one works out perfect because 0 is one of the numbers on my scale. But if 0 wasn't a number on your scale, you would have to estimate, well, where would 0 be? If it was, if this was negative 30 and this jumped all the way over to 15, we'd have to say, well, the 0 is over here somewhere, and you'd draw your vertical scale bit roughly where you think it would go. So I'm going to actually use the line feature here. And I'm going to put a vertical line down. I'll move it over where it belongs here in a second. So this go through there. And we said that it's going to be between 0 and -4. So if you look in your scale up here, you need to use the y values 0, -2, and -4. So when I scale this off down here, just make sure I can plot all those points. So I'm going to go. So I've got 0. So let's put down here, just so I know. That's going to be the bottom, -4. Cut that roughly in half. There's your -2. All right, so let's go to our table and plot those 5 points. So I've got -3, 30, -2. So -30, -2, roughly there. And then I've got 0, -4. 0 and -4. See, there. 30 is again at -2. There. 60 is at 0. And 90 was also at -2. Okay, so this, I'm just going to draw a line in here for a second. This line right here remember, has a name. That line that I just drew is your sinusoidal axis. Dots or not. Could have made them a little bit darker maybe. So we had a dot here. Next dot was here. There it is there. There. And now all you're going to do, now this is probably going to be a disaster here with me trying to use this stylus on the laptop, but on your page, don't do it like a connect the dot, like with these jagged straight lines. You know it's going to be a sinusoidal wave. So you got to make sure your graph models the pattern that we know it's supposed to. So I'm going to try and do this now with a nice smooth sinusoidal pattern. So it's going to come down like so, up through here, down through there. And then at the ends of these, because it keeps going, you're going to put arrows. That wasn't too bad, actually. And that would be what they mean by sketching one full cycle. So there is your first sketch of a sinusoidal relation. It had its, there's its sinusoidal axis. Amplitude was 2. Period, look, let's check the period. It started at -30 and it finished at 90. So on that scale, from -30 to 90, that's a total of 120 degrees, which is perfect because that's what we had said the period of this graph was going to be. All right, so there you have it. That's how we're going to sketch these things. And that's what we need to get good at in the next few examples. Now, when you're starting to feel like you're kind of getting the hang of things, you'll probably want to pause the video first and then try it on your own. Oh, sorry, I know what I was going to do. So when you start doing these at home, you say, well, I wonder if I did that right. What you're going to do is you're going to just go to Desmos and you're going to type in the equations. I'm just going to jot it down here so I don't have to. So it's y equals -2 sine 3 theta plus 30 minus 2. All right, so I have Desmos all ready to go here again. So remember we talked about using this wrench to set up your graph. So I want to basically make this graph look exactly like what I had on my smart file back there. So I want the x-axis. Remember it started at -30. It was done at 90. And remember, step is another word for scale. And our scale was 30-degree blocks. The y-axis, you remember it went up to 0. I'm going to go a little bit higher. So I'm going to make it go to 1. And I'll make it go down to -5, let's say, -5. And I want to be in degrees. All right, here we go. Y equals, so actually type in using the keyboard, sine. You need to put a bracket here. So sine 3. Now another bracket. This is your phase shift. I just like to use x. You don't have to use theta. I'm just going to use x plus 30. Close that bracket. Close that bracket. And now you put your vertical shift in. And when I type this, on the graph here should appear the graph the same as we sketched on our smart notebook. Something what's wrong with my scales? Yeah, I messed up something here. Let me check this. Oh yeah, so this should have been -6 or -5. -5. We're in degrees. Let's try that. That did work. I forgot to save it. -5. Steps in degrees. Oh, I know what's wrong. I get these backwards. Smallest one's got to be first. So -5. And then this should be the 1. That makes more sense. Okay. So there is, oh, I forgot there was a -2 out front here. So -2. So if you were to look at our page back on the smartboard, compare it with this, which you can actually do. One of the options here, let me think. No, sorry, it's over here. Anyway, you can actually copy this graph. I could, and then take it over to here, paste it on our notebook and look at it, but it's exactly the same. That's what we ended up with right there. All right, so that's where you're gonna be able to check your answers. Just on your phone, type them into Desmos, and you can use that to verify your answers. And again, the key is to set up your window here to look exactly like the graph you made on your page. All right. Here's our second example. So let's look at this one. Let's fill in our chart first. All right, so the domain, that's always pretty much the same thing. Theta can be any element of the real numbers. The range, this one you got to think through. So you got 3, which means it's going to go up to 3 and down to -3. However, you also have a vertical shift of up 2. So that's going to move this up 2, and it's going to move this up 2. Well, if this one goes up 2, it's going to be at -1. This one goes up 2, it's going to be at 5. So there's where the graph's going to end up at the very end, between -1 and 5. So -1 to 5. The amplitude is always the number out in front of your trig function, so it's always positive, 3. The period is normally 360, but in this case, it's going to be 360 divided by that k value. So it's 360 over 2, which will tell me the period is 180. The phase shift. Phase shift is always right here, so it's going to go right. Remember, it's the opposite sign in this one, so right 135 degrees. And what's going on here? Not that though. Let's get rid of this. Our vertical, I don't want this either. Our vertical translation, go up here, is up 2 units. So this is up 2 units. And the sinusoidal axis, remember, is the one that's always in the middle of your high and low value. And with a function that's presented like this one was in standard form, it always will match up with your vertical translation. It's always y equals that number. So my sinusoidal axis, the wave or the line that cuts the wave in half, would be passing through y equals +2. All right, so now we're going to take that same trig function, which I've got here in the next slide, and we're going to graph it. So now again, I've got some of the information all laid out for you. You got to understand that on a test or an exam or something, all that would appear would be the function. That's it. And you would have to come up with all this. So I've got it all laid out, just kind of what we would call scaffolded for us. just to make things go a little bit quicker. Okay, so this time it's a cosine function. So the cosine function, you need to know the pattern. This is the pattern of the cosine function. So there's your 0, it's at 1. Remember, this is 1, the high point, minus 1 is your low point. So that would be 0, this would be 90. The middle of it would be 180. This would be 270. And then the end is 360. Well, if I get my base points off my graph, there's your graph up there, just look at it. At 0, the y value is 1. At 90, the y value is 0. At 180, the y value is -1. At 270, the y value is 0. And at 360, the y value is 1. So then we're going to write a mapping. You can see this is a pretty kind of algorithmic process. You follow the same steps every time. So now I'm going to write my mapping. So theta, comma y will get mapped to. I'm going to take 1/2 of all the angles. I'm going to move them right. So I'm going to add 135 degrees. I'm going to multiply the y values by 3. And then I'm going to move them up 2. So this mapping, when applied to this base set of points, is going to give us our new. So remember how it works. These points get fed into here. You, in turn, then spit out the new points, and you plot those 5 new points. So here we go. The first one, we're going to fill 0 in for theta. So 1/2 of 0 is 0 plus 135 is, in fact, 135. The y value. So if I put 1 in here, 3 times 1 is 3. 3 plus 2 is 5. 90. 1/2 of 90 is 45. Add 45 to 135, and you're going to get 180. And do 0. 3 times 0 is 0, plus 2 is 2. 180. 1/2 of 180 is 90. 90 and 35 is 225 degrees. This angle, or sorry, not this angle, this y value will be, so -1 is going in here. -3 plus 2 is -1. You can see we're going up by 45 each time, so I should be able to keep the pattern going now. So add 45 to that one, you're going to get 270. Add 45 to that one, and you're going to get 315. Now let's check these ones. Well, 0 I've already done here, so I'm going to get a 2. +1 I've done up here, so I'm going to get 5. Let's just verify with what we found in the last slide when we filled in our chart. So let's check our range. Biggest number is 5, lowest number is -1. So the graph runs between -1 and 5, which we had. It starts at 135. It finishes at 315. Well, 315 minus 135 is 180 degrees, which is what we determined the period was going to be for this graph. So it takes 180 to complete the pattern. So we're in good shape right now. Let's go down here. Now remember, it's easier to not use grid paper, so I'm just going to delete this. I don't want that grid paper in there. I'm going to get rid of this. Well, and I always like to wait until the end to put the y-axis on. Okay, so we're going to, one thing you'll notice in this one, there's no negative numbers here, and it starts at 135 on my horizontal axis, which is fine. But just leave yourself a bit of room here where you can put your vertical axis, because it's going to be to the left of your point. I'll show you how we're going to deal with that in a second. So we are going to, let's say I start here, end here, cut it in half, that in half, cut that in half. So there's your start, 135. 315 was the end. And then 270 was here. 225 was here. And this one was 180. Well, the problem here is the y-axis, well, it would actually be way over here somewhere off the left of the page. Well, I don't want to do that, so I'm going to actually put my y-axis in just over here, like so. Now remember, it goes up to 5, so you're going to have some room up here. There's my y-axis. And I'm sure you've seen this before. All we're going to do is, because this isn't really the scale, so all you do is you put a little compression symbol like this here to indicate that you've basically taken this and squished it over to the right. That's all that little symbol means, is that this part here isn't representative of the scale that's on the go here. Now you can get your y values put on here. So you got 5. The lower number, I think, was -1. So I'll just put that, let's say, there. And then 2 would be roughly in here. You don't, and again, you don't have to worry about scaling this off either, as long as the distance from here to here doesn't have to be perfect, but it should be about the same distance as it is from there to there. Okay, here we go. Start plotting points. So the first point is 135, 5. So 135, 5. I'm trying to make it a little darker this time. There we go. Then it's 180 is at 2. So 180 is roughly here. 225 is at -1. Right there. 270 is up at 2. And 315 is up at 5. Now we're going to connect those. And again, don't make a straight line, make it look like the letter V. We're letting you only use 5 points, but to do that, we're giving you the benefit of the doubt that you know enough about the situation that it's going to be a sinusoidal graph, and you're going to make it look like a sinusoidal graph. All right, so I'm just going to start here, come up, down through here, turn in my wave, back up this way, try not to make it too straight, make a wave that goes down this way, arrow here, arrow here. Now, one little thing to watch for is that I find students will get these points and then they'll come to this point and all of a sudden they'll get to here and they'll shoot the graph up this way and put an arrow on it. Well, that's not right, because the graph is never going any higher than 5. So you got to make sure at these endpoints you're turning it down before you put the arrow on it. Don't put that little piece up there like I just did. The other thing that you got to watch for is that this piece here has been compressed. So you can't do this. You can't take this and just keep it going and cross it and say, oh, there, it's going to cross the axis there, because that's not where it would cross the axis. Because, I mean, this graph could have come down and up here because we're not showing what's happening over here in the compressed region. So it's important that you don't extend that across this axis when you've compressed it down here, because that will not be the actual place it's crossing the axis. Okay, so just go like I did there, slightly past it, turning down, slightly past it, turning down. Again, as smooth as I can do here with this stylus. And that would be our graph. Finished. I'm going to do one more. And we'll look at this. Well, this is a good one to use as our example. So the problem with this one, so I'm just going to kind of sketch it. You can see here it's just a blank slate. I just gave you the function and said, good luck. Well, the first thing I need to do is, this doesn't look like the first two that we did. It's not in the form y equals. So the first thing we're going to do is rearrange this to make it look like our standard form. Well, there's several ways to do that. I'm going to start, and I'm basically just going to whittle away at this stuff over here until it is all moved to that right side. So the first thing I'm going to do is I'm going to double this, and that'll get that to cross out. Well, if you're going to multiply the left side by 2, you need to multiply the whole right side by 2. Now, this is all considered 1. Multiplying by 2 will never impact the argument in here. That's called the argument of your trig ratio. So when you multiply by 2, all it's going to do is change that number. No effect whatsoever on those. Now, here's what students do wrong. They say, oh, there, I multiplied by 2. Well, that would take care of this one, but you also have to multiply this one by 2. Then everything's getting multiplied by 2. So then it becomes y plus 1 equals 6 cosine of a half theta minus 90, and then plus 4. Getting closer. So now, again, I want to get y equals. So I'm going to take away 1 from both sides of the equation. Now, it's not like multiplication. You don't have to take away 1 from every term. You have to take it away from both sides of the equation. So y will equal, The only thing that's going to affect is this number right here. So this is going to stay 6 cosine of 1/2 theta, subtract 90. When I take away 1, that's going to become plus 3 now. All right, so we're getting closer to the point where we could identify our mapping to go with this. One small issue here would be many students might get to here and say, okay, I'm good. This graph is going to have a k value of 1/2, which is actually going to make the graph double its width. So it's going to actually take 720 to make one full pattern, which again, that makes no difference to us. We'll deal with what we have to in terms of the scale. But here's where students will go wrong. They'll say, so it's going to shift to the right 90, which would be incorrect. If you notice back on the last one, I'll just jump back the last slide. Notice how there was a 1 in front of the theta when I identified this horizontal phase shift. Any coefficient of theta must be factored out. In the first two examples, it was done for you. In this example, we need to do that. So I need one more line here. So y equals 6 cosine, put a bracket. You must factor out the 1/2 theta. Now, what am I going to put here? Well, whatever you put here, when you multiply it by 1/2, you got to get that number up there because this bracket has to be the same as what's up here. So this is going to have to be a 180. And just double check. 1/2 times theta, 1/2 theta. 1/2 times negative 90, negative 90. So I know I'm good. That's right now. And then I still have my plus 3. So now you can see that the phase shift is actually 180 to the right, not 90 to the right. Okay, so we've got a base function of cos theta. So that's here for us. Let's set up, I guess I do have all the charts here. So let's set up our, the domain of this one now. Theta could be anything. It's always a freebie, that one. Now the range, let's look at my graph. See if I can do it in my head here. So 6 is going to make it go, I'll draw it over here. So 6 is going to make it originally be 6 to minus 6. And then a plus 3 is going to move this up 3. So it'll be at 9. It's going to move this up 3. So it'll be at minus 3. So there's your range from negative 3 to 9. So my range is negative 3 to 9. My amplitude's always the number out front, so it's 6. Remember, always positive, even if that had been a negative. 6. The period. So the period is always 360 divided by that number. Well, this time it's a fraction. So when you go to do your period, it's going to be 360 divided by 1/2. Well, to divide by a fraction, you actually multiply by the reciprocal, which is going to give us 720 degrees. So it's going to take twice as long to make the pattern as it used to. Phase shift, that's the one we had talked about a moment ago. It's 180 to the right. Again, look up here. There's your phase shift, 180, right. And vertical translation, that's this number right here. So up 3. This is going to go up 3. And your sinusoidal axis, I don't even got to look. It always matches up with this. So up 3, it's normally at y equals 0. So it's moved up 3. It's now at y equals 3. There's your sinusoidal axis. Okay, go over here. Let's write our mapping first, I guess. Okay, so go right here so I can see. I'll move the box up so I can see everything. Okay, so here is my mapping. Theta y will get mapped to. So we are going to take, so normally it's the reciprocal of this. So if that was a 5, it'd be 1/5. But because it's a fraction, we're actually going to double all the x's or thetas. which makes sense because we said the period is going to be twice what it used to be. We're going to move them all to the right, 180. The y values are all going to get multiplied by 6, and they're going to get moved up 3. All right, because it's cosine, here's your picture of cosine over here. Now we're going to fill in the base points down here. So cosine, I was accustomed to the, I know the graph's right over there, but just quickly sketch, just go whoop, like that. Say 0, it's at 1. 90 is at 0. 180 is at -1. 270 is back at 0. And 360 is back up at 1. Okay, remember that's theta. Okay, so we are going to take twice theta and add 180. So 0 plus 180, that new point is going to be 180. The y value is going to be 6 times 1 plus 3. It's going to be up at 9. 90. So twice 90 is 180 plus 180. That's 360. 0. So 6 times 0 plus 3. That's going to give me 3. 180. So 2 times 180 is 360. 360 plus 180 is 540, which would be right. We're adding 180 each time. Let's keep going. So 540 and 180 is 720. And then 720 and 180 is 900. Let's see if that makes sense. So if I start at 180 and finish at 900, that's a total of 720, which does make sense because we said the period was going to be 720. Let's fill these in now. So -1, 6 times -1 is -6 plus 3. That's -3. 0 I already did. I know I'm going to get 3. And 1 I did already up here. I'm going to get 9. Let's check if these make sense. Smallest number I see in my y values is -3. Biggest number is 9. That makes sense with what I identified over here. We're good to go. So we're ready to draw this one. So here's your horizontal scale here. Here's your vertical scale. So kind of look things over. I got to go up to 9 and down to -3. So I'm going to have to make sure I get enough room to do so when I draw this. Again, I'm not going to use the grid paper. I just find that harder to do to make everything work. We'll get rid of the grid paper. I'm going to get rid of the vertical axis. Right, I don't want that on there in the beginning. I'm going to put it on at the end. All right, so this time, again, I started at 180. Here. So I started here, let's say. I'm going to end the cycle here. Cut it in half. Cut that in half. Cut that in half. There's your equal points. It was 180, and our scale was 180. So then this was 360. This was 540. This was 720. And this one was 900. Now, this one works pretty nice where I could actually not use the compression symbol if I didn't want to. As long as so if you look at that distance, that's 180. So as long as I go over that, which is pretty close to right here, so I'm just going to put my axis running down. Now remember, I got to go up to 9, so I'm over there. And you can always use a scale, because you don't have to actually count up to 9. I didn't have to make it that high if I didn't want to. So I'm going to this kind of pushed over, but anyway. So there's my top number, 9. There's my lower number, -3. So the middle here then, roughly there, that must be my 3. So I always want that distance from the bottom to the middle, and then from the middle to the top, you want those to be the same. All right, here we go. Start plotting points. So 180 was at +9. So 180 is up here at 9. 360 was here at 3. 540 was at -3. There. 720 was back up at 3. 900 was up here at 9. So there's your 5 dots. Now notice I didn't use a compression symbol because this is pretty close to the same width as these, so I don't have to use that. And each one of these blocks is 180, or 180 back to there would be at 0, so it's all good. So I'm going to, this one actually would hit right here because of the way the pattern's going. But anyway, I'll just go try and make my smooth curve here best I can. So up, missed that one, but that's all right. Down, up, and down. And notice how I missed the points ever so slightly. And again, it's hard to do this with a stylus, but if you're doing this by pencil, when you get to here, don't at the last second jut in, I don't want to miss that point. I want it to look, and that's not great either, it's pretty shaky looking, but I want that to look like a sinusoidal relationship, the wave pattern that we've talked about. All right, so those three examples should get you pointed in the right direction for how to do sketches of sinusoidals. And what you're going to do now, you have the smart files. So if you notice in the next coming slides, there are some examples. So I would suggest you try a couple of these on your own now, and then type it in your graphing calc or your Desmos, sorry, on your phone, and just have a look and see how you make out. And if you have any questions or concerns, you can contact me. I'll come back in another day or two and do another video with a couple of these. You do run into radian measure in a little bit, so we might look at what those look like specifically, but that should be enough information to at least get you to the point now where you can start doing some actual questions. Good luck.